Before engineering a piece of heavy-duty machinery, like a motorized pool lift designed to safely lower a person into the water, you have to prove the mechanics actually work. To simulate that complex physical motion on a screen, engineers rely on basic geometry, translating rigid steel bars into strict mathematical wireframes. If we strip away the physical environment entirely, we can focus purely on the geometric relationships driving the machine. Every moving simulation requires a starting position. We establish a single, unmoving anchor, point O, representing exactly where the lift is bolted to the deck. This is our absolute origin. Every other length and moving part is measured from this stationary position. The power source of the entire machine is the actuator segment, marked here from O to P. As this section extends and contracts, it drives the rest of the mechanism. This interface controls variables. Dragging the red slider changes the driver length, the primary mathematical input controlling position. That input transfers to a four-sided mechanism defined by points D, G, H, and F. This main parallelogram structure attaches to the primary lift arms. This specific mechanical arrangement does one job. It forces the seat bracket to remain perfectly vertical, while the main support arms swing upward and downward in an arc. If this structure were a single rigid triangle instead of a parallelogram, lowering the lift into the water would tilt the passenger forward right out of the chair. Notice the web of overlapping dashed lines. These geometric circles act as mathematical constraints. A circle's constant radius forces the simulated metal bars to maintain fixed lengths. Where two circles intersect, the math creates a precise, moving hinge. Now we need to attach the seat. We have point G, and we need to attach a rigid plastic arm that is exactly 7 units long to determine where point J belongs. What specific tool guarantees that point J stays exactly 7 from G, no matter how the rest of the simulation moves? We define a circle. By setting the center at G and imposing a strict radius of 7, the software ensures that distance never changes. The lower half of the chair requires a different approach. A footrest must attach to the main seat base, defined by points J and K. By applying a specific rotational angle, here 136 degrees, we permanently lock these individual points together into a single rigid shape. This diagram shows the completed pool lift model in its fully extended position. With the slider set at 6.56, we can see the upper physical limit of the lift, and this diagram shows the lowest position. Contracting this single actuator segment smoothly pulls the entire mechanism down to water level. It operates on a continuous mechanical chain reaction. The actuator pulls the frame, the circle constraints force the hinges to travel in precise arcs, and the parallelogram prevents the passenger from tilting. The exact rules used to build this model can be applied to almost any moving structure. You can approach any mechanical project using 4 steps. Anchors establish your starting point, sliders drive your variables, circles constrain rigid lengths, and parallelograms lock orientation. Once you organize these constraints, you can accurately model anything from a desk lamp to a mountain bike suspension.